The MEWL benchmark, designed to assess the ability of machines to learn word meanings in grounded visual scenes, draws inspiration from human cognitive tools such as cross-situational reasoning, bootstrapping, and pragmatic learning. This benchmark comprises 9 tasks that mirror children's core abilities in word learning, aligning with theories in developmental literature. It highlights the disparities between human and machine word learning, emphasizing the necessity for machines to mimic human-like few-shot word learning capabilities. Machine word learning, MEWL, is a benchmark designed to evaluate machine word learning in grounded visual scenes, encompassing humans' core cognitive toolkits in word learning. The benchmark comprises 9 tasks, covering basic attribute naming, relational word learning, number word learning, and pragmatic word learning. Each task consists of 6 context images and corresponding descriptive novel words or phrases, requiring agents to rapidly understand the meaning of novel words from context and select the option that best matches the target query image. This simulates children's fast cross-situational word learning. The MEWL benchmark highlights the importance of human-like word learning in machines, providing a comprehensive evaluation of multimodal and unimodal models. The results reveal that pre-trained vision language models struggle to learn word meaning with only a few examples, significantly lagging behind human capabilities. This underscores the need for machines to develop more human-like word learning abilities, particularly in scenarios with limited examples. The MEWL benchmark serves as a valuable tool for assessing and improving machine word learning, bridging the gap between human and machine language understanding. Machine word learning, or MEWL, is a benchmark suite that surpasses existing benchmarks in 6 dimensions: multimodality, few-shot learning, referential uncertainty, relational reasoning, pragmatic reasoning, and human baseline. It focuses on various aspects of word learning, including attribute, relational, numerical, and pragmatic word learning. MEWL requires cross-situational learning with referential uncertainty, which is a crucial aspect of human-like few-shot word learning. The benchmark suite has a significantly larger scope with 37,800 questions compared to existing benchmarks. It is designed to evaluate alignment between humans and machines, covering aspects such as learning novel words, bootstrapping, and pragmatic reasoning. The 9 tasks in MEWL are inspired by human word learning methods, including cross-situational learning, bootstrapping, and pragmatic word learning. The machine word learning, MEWL, framework is designed to investigate how machines learn word meanings across various few-shot scenarios with referential uncertainty. It comprises 4 categories of tasks: basic naming, bootstrap relational word learning, learning number words, and pragmatic word learning. Each episode consists of 6 context images and corresponding utterances, requiring agents to choose the correct utterance matching the query image. The framework includes 27,000 problems for training, 5,400 for validation, and 5,400 for testing, evenly divided among the 9 tasks. The problems are designed to ensure referential uncertainty, with novel words and concepts varying across episodes. This setup allows for the assessment of word learning capability in the context of few-shot learning rather than plain memorization. Machine word learning, MEWL, is a suite of tasks designed to evaluate an agent's ability to learn novel words in various contexts. Inspired by human language acquisition studies, these tasks probe different aspects of word learning. The shape task requires agents to learn novel words representing different shapes, with each context image featuring one object and a corresponding word. The query panel tests the agent's ability to choose the correct word for a given shape from 5 options, including 2 distractors. The color task studies learning novel words representing colors, using 8 distinctive colors in each episode. The material task is similar, focusing on naming 3 distinct materials. The object task probes cross-situational word learning for objects, considering size, color, material, and shape. The composite task focuses on learning compositional multi-word phrases, using syntax to bootstrap the word learning process. Agents must learn novel words representing basic attributes and phrases sharing the same syntax in an episode. The relation task investigates agents' capability of learning relational words, such as left, right, front, and behind, which are acquired later than object-centric words in humans. The bootstrap task flips the direction of the composite task, inferring objects' names using familiar relational words. The number task focuses on learning numerical words from 1 to 6, requiring agents to count objects and determine the word-number mapping. Finally, the pragmatic task inspects the agent's pragmatic word learning capability, inspired by social pragmatic theories of human language acquisition. The MEWL framework is introduced, a pragmatic scenario for machine word learning where rendered hands point to objects with unique attributes. Each image contains 3 objects, with a finger pointing to a referred object identifiable from context. The goal is to learn novel attribute words and test them in query images. Ground truth scene information is provided, including task name, answer choice, word-to-concept mapping, object types, and coordinates. Contemporary models are examined on MEWL, formulated as a few-shot vision language learning problem. Models are categorized into multimodal, pre-trained on large-scale image caption pairs and fine-tuned on MEWL, and unimodal, using a caption-then-classify paradigm. Multimodal models include CLIP, Flamingo 1.1b, and ALLO, while unimodal models employ language models like GPT 3.5 and BERT for classification. The experimental setup involves training and testing models on the MEWL dataset, comprising 9 tasks for evaluating word learning capabilities. A human study is also conducted, where participants complete questionnaires based on MEWL tasks to establish a baseline for comparison with machine models. The machine word learning (MEWL) task was evaluated using various baseline models and human participants. Table 2 presents the performance of these models on the MEWL task, with results visualized in Figure 3. The best vision language model, Flamingo 1.1b, achieved an average performance of 41.0%, which is approximately half that of human participants, who scored 73.7% on average. In contrast, vanilla transformer models with CLIP features performed poorly, achieving only random-level performance on all tasks, with an average score of less than 20%. ALLO, an object-centric representation model, improved performance to 26.8%, but its limited model capacity and lack of pre-training may hinder its performance. Task-specific results reveal that vision language pre-trained models perform relatively well on basic attribute naming tasks, such as shape, color, and material, but struggle to generalize to object relations and pragmatic cues. Notably, the Flamingo model demonstrated some ability to solve bootstrap and number tasks, possibly due to its language model-based architecture, which captures syntactic cues and understands familiar words to facilitate word learning. Unimodal language models, such as fine-tuned BERT and GPT 3.5, achieved outstanding performance on object-level tasks, with BERT scoring an average of 68.3%. The human participant pool consisted of 271 individuals, recruited from Prolific, an online participant pool, who completed 9 tasks and were paid an hourly wage. Responses from participants who failed attention checks or were outliers were removed, leaving 217 valid responses for analysis. The machine word learning (MEWL) framework is designed to assess word learning capabilities in various models, including BERT and GPT 3.5. This study evaluates these models on 3 distinct tasks: basic naming, relational, and pragmatic word learning. The results indicate that fine-tuned BERT excels in pragmatic tasks, whereas GPT 3.5, without fine-tuning, underperforms. This suggests that certain capabilities can be acquired through task-specific fine-tuning. A human study confirms that MEWL effectively captures core cognitive skills involved in word learning. In the discussion section, multimodal and unimodal models are compared. Text-based models with ground truth captioning generally outperform pixel-based ones, demonstrating the importance of linguistic context in word learning. Interestingly, unimodal agents can surpass multimodal ones, implying that the conceptual role in unimodal language models might be acquired differently from humans. The page concludes by highlighting the limitations of current machine word learning capabilities and the need for further research to enhance these abilities. The study's findings provide valuable insights into the development of more effective language models and their potential applications in natural language processing and cognitive science. Machine word learning, or MEWL, is a novel benchmark for evaluating human-like few-shot multimodal word learning with referential uncertainty. Inspired by developmental studies on children's word learning, MEWL comprises 9 tasks that assess machines' core cognitive toolkits, including cross-situational reasoning, bootstrapping, and pragmatic learning. This comprehensive suite of tasks simulates real-world word learning scenarios, allowing for a thorough examination of machines' word learning capabilities. The authors apply MEWL to contemporary multimodal and unimodal pre-trained models, revealing that unimodal large language models demonstrate few-shot word learning capabilities on certain subtasks, although they still fall short of human-like performance. In contrast, multimodal vision language models struggle with most tasks, with the exception of the largest language model-based Flamingo, which performs better. The results highlight a misalignment between machines and humans' few-shot word learning capabilities, emphasizing the need for further research. MEWL is poised to initiate a journey towards building multimodal agents with human-like few-shot learning capabilities, with open problems and opportunities including the development of machines that can learn from uncertainty, the role of social pragmatic learning in machine learning, and the potential for human-like word learning to yield human-like word meaning. This page presents a comprehensive list of research papers that have made significant contributions to the field of artificial intelligence. These studies, conducted by leading researchers and institutions, cover various aspects of AI, including machine learning, natural language processing, and robotics. The first paper, titled Deep Blue, a grandmaster-level chess computer, discusses the development of an AI system capable of defeating a world champion in chess. This achievement was made possible through the use of advanced search algorithms and parallel processing techniques. Another notable study, BERT, Pre-training of deep bidirectional transformers for language understanding, introduces a new language model that has achieved state-of-the-art results on numerous natural language processing tasks. This model uses a pre-training method called masked language modeling, which allows it to understand context and relationships between words more effectively. In addition, AlphaFold, using AI for protein structure prediction, presents a groundbreaking approach to predicting the three-dimensional structure of proteins using deep learning models. This research has the potential to revolutionize the field of biochemistry and drug discovery. Furthermore, the Robotics Operating System, ROS, a framework for building robot applications, describes an open-source software framework designed to simplify the development and integration of robotics algorithms. ROS provides a set of tools, libraries, and conventions that aim to encourage code reuse in robotics research and development. These papers, along with others listed on this page, demonstrate the breadth and depth of AI research. They highlight the innovative methodologies and technologies being developed to advance our understanding and capabilities in this rapidly evolving field. The research focuses on machine word learning, particularly in the development of relational category knowledge, word meanings, and compositional actions. It underscores the importance of shape and texture in early lexical learning and the role of pragmatics in children's word learning. The study also explores the development of systematic generalization in perception, syntax, and semantics, as well as learning mechanisms in physical reasoning. Datasets and benchmarks are emphasized for advancing our understanding of human and machine learning. Machine learning has revolutionized the field of natural language processing, particularly in word learning and concept development. Researchers have employed various methodologies to improve language models' ability to learn and represent words and concepts. One key concept is the concept of word embeddings, which involves mapping words to vectors in a high-dimensional space. Word2Vec and GloVe are two popular word embedding algorithms that have been widely used in natural language processing tasks. These algorithms capture the semantic relationships between words, enabling language models to better understand the meaning and context of words. Another crucial aspect is concept development, which involves the formation of abstract representations of concepts from raw sensory data. This process is critical in machine learning, as it enables models to recognize and generalize patterns. Researchers have employed various techniques, including clustering and dimensionality reduction, to develop concepts from large datasets. One novel approach is the use of cognitive architectures, which are inspired by human cognition and learning. These architectures are designed to mimic the human brain's ability to learn and represent concepts, enabling language models to develop more nuanced and abstract representations of words and concepts. The paper also explores the role of attention mechanisms in language models, which enable models to focus on specific parts of the input data when making predictions. This is particularly important in tasks such as language translation, where models need to attend to specific words or phrases to generate accurate translations. The researchers also discuss the limitations of current language models, including their inability to reason abstractly and understand context-dependent semantics. They propose future work in developing more advanced cognitive architectures and attention mechanisms to overcome these limitations. Overall, the paper provides a comprehensive overview of the methodologies and concepts in machine learning, highlighting the importance of word learning and concept development in natural language processing. Understanding human cognition and perception is crucial for developing advanced artificial intelligence models. In machine word learning, Xu and Tenenbaum's 2007 study demonstrated that word learning can be viewed as Bayesian inference. More recently, Xu et al.'s 2022 study introduced evaluating scientific thinking, or EST, to assess scientific thinking in artificial agents. Visual reasoning is another critical aspect of AI research, with Jiang et al.'s 2019 study introducing Raven, a dataset for relational and analogical visual reasoning. Their 2021 work explored abstract spatial temporal reasoning via probabilistic abduction and execution, while their 2022 study focused on learning algebraic representation for systematic generalization in abstract reasoning. Language models have also seen significant advancements, with Zhang et al.'s 2022 work on OPT, or Open Pre-trained Transformer Language Models. Additionally, their 2020 study introduced machine number sense, a dataset of visual arithmetic problems for abstract and relational reasoning. Cognitive AI with human-like common sense is another area of research, as seen in Zhu et al.'s 2020 study, which proposed a paradigm shift towards cognitive AI with human-like common sense. Furthermore, Zhuang et al.'s 2021 study, published in the Proceedings of the National Academy of Sciences, presented unsupervised neural network models of the ventral visual stream. These studies collectively emphasize the importance of integrating cognitive science principles into AI development to achieve more human-like intelligence. By understanding human cognition and perception, researchers can develop more advanced AI models that mimic human thought processes. The MEWL dataset is generated by combining three shapes: cube, sphere, and cylinder, each assigned a unique novel word. To create context, a shape and its corresponding word are selected, along with properties like color, size, and material. The query panel features a shape for testing, accompanied by 3 novel words and 2 dummy words as candidate options. The color task involves 8 colors, with 3 randomly selected for each episode. Materials such as rubber, metal, and glass are also included, focusing on object quadruples comprising size, color, material, and shape. The object task constructs images and utterances around these quadruples. The composite task is designed to learn compositional multi-word phrases using syntax, while the relation task probes agents' capability in learning relational words like left, right, front, and behind. The bootstrap task infers objects' names using familiar relational words, assessing the agent's ability to generalize and learn from context. This refined dataset enables researchers to evaluate the performance of language models and their ability to understand complex concepts, relationships, and compositional language structures. Machine word learning is the focus of this research, specifically targeting the learning of number words from 1 to 6. To achieve this, context images are designed featuring varying numbers of objects, each paired with novel words. In the pragmatic scenario, rendered hands are used for pointing gestures, requiring agents to understand the mapping between words and numbers, as well as attribute-based object identification. In the unimodal language model, ground truth scene captions serve as input, providing detailed descriptions of objects' attributes and spatial relations. For instance, Figure A1A illustrates a caption that elaborately describes 3 objects, whereas Figure A1B concentrates on the spatial relationships between objects. Figure A1C demonstrates the pragmatic task, where the agent must identify the object being pointed at. The text input is a combination of prompts, context captions, and query image captions, all working together to solve the problem. By leveraging this multimodal approach, The agents can develop a deeper understanding of word number mapping and object identification, ultimately enhancing their machine word learning capabilities. The experimental details for the baseline models used in the paper are discussed. For vision language models, images and corresponding texts are used as input. For language-only models, images are first parsed into full scene descriptions using a captioner, and then scene descriptions and utterances are used as input. The CLIP model utilizes a pre-trained image encoder, and text features are calculated using the text encoder or token embedding. The resulting features are concatenated and passed through a 6-layer transformer model. The ALLO model employs the Monet architecture, using the mean of the object feature as the visual input for the transformer. The Flamingo 1.1b model is used for MEWL tasks, formulated as a multiple-choice problem with a binary classifier head. Hyperparameters for training are detailed, including epochs, learning rates, and optimizers. The MEWL optimizer, a machine learning optimizer employed in the experiment, is implemented using the ATOM optimizer with hyperparameters beta 1 equals 0.9, beta 2 equals 0.999, and e equals 1 times 10 minus 8, alongside a linear learning rate decay and a batch size of 96. For few-shot multiple-choice question answering, the authors utilize the GPT 3.5 model provided by the OpenAI API. They formulate the task by concatenating image captions and utterances as inputs, constructing 5 input prompts for GPT 3.5, and selecting the answer with the largest log probability. In contrast, the BERT model is used following standard practice for multiple-choice question answering. Ground truth captions are generated, question inputs are constructed, and a BERT base model is fine-tuned on the training set for 200 epochs with a learning rate of 5 times 10⁻⁵ and an ATOM optimizer. A human study is conducted, recruiting 271 participants from Prolific to complete 9 tasks. Participants are paid an hourly wage, and the study is approved by an IRB. Responses from participants who failed attention checks and outliers are removed, resulting in 217 valid responses. Data processing and statistical analysis methods involve removing responses from participants who failed attention checks and performing Grubbs tests to remove outliers. A one-tailed t-test is used to determine if one task is significantly easier than another, with a significance level of p less than 0.05. The results of human performance and t-tests are presented in tables A1 and A2, respectively. Table A1 displays the performance of humans on the MEWL tasks, with average scores ranging from 48.7 to 93.9. Table A2 presents the p-values of human results, indicating whether one task is significantly easier than another. The results show that humans perform differently on various tasks, with some tasks being significantly easier than others. The MEWL framework is demonstrated through 2 task examples, showcasing its versatility in machine word learning. In the first example, the query, shape desit bon payments bon desit, is presented, with options, payments, tivitum, liars, desit, and bon. The ground truth reveals that the correct answer is payments, which is mapped to the concept of a cylinder. The word concept mapping illustrates the learned relationships, where bon corresponds to a sphere, payments to a cylinder, and desit to a cube. In the second example, the query, subno tis tamar subno tis, is presented, with options, tis, tamar, subno, plano, and iespen. The ground truth indicates that the correct answer is tis, which is mapped to the concept of a sphere. The word concept mapping reveals the learned relationships, where tamar corresponds to a cylinder, subno to a cube, and tis to a sphere. These task examples demonstrate the MEWL framework's ability to learn and generalize word concept mappings, highlighting its potential in machine word learning applications. The framework's performance is evaluated through its ability to correctly identify the ground truth and learn accurate word concept mappings. The results underscore the significance of the MEWL framework in enabling machines to learn and understand human language, showcasing its ability to generalize and adapt to new word concept relationships. In the realm of machine word learning, a novel approach is proposed to understand and map word concepts in a visual recognition task. The primary focus is on developing a model that can effectively differentiate between various color terms and their corresponding visual representations. This model, known as MEWL, machine word learning, aims to bridge the gap between linguistic and visual representations of words. The page introduces 5 color terms: agemo, ernmo, unap, romu, and posden, which correspond to blue, green, gray, brown, and blue colors, respectively. 2 queries are presented to demonstrate the model's ability to learn and apply these color word mappings. In the first query, the model is given options agemo, unap, kuru, inside, and ernmo, and must choose the correct color term for the provided visual representation. The ground truth indicates that unap corresponds to the color gray. In the second query, the model is presented with options posden, noden, priv, romu, and lay, and must select the appropriate color term for the given visual representation. The ground truth reveals that posden represents the color blue. This page highlights the potential of the MEWL model in learning and applying word concept mappings, particularly in the context of color recognition. By leveraging visual and linguistic cues, the model can effectively differentiate between various color terms and their corresponding visual representations. This research contributes to the advancement of artificial intelligence and machine learning models, enabling them to better understand and interpret human language and visual data. The machine word learning (MEWL) framework, a pivotal step in the development of more sophisticated word learning models, is centered around the material properties of words. This approach categorizes words based on their material properties such as glass, metal, and rubber, utilizing a word concept mapping technique. The accurate identification of materials for effective word learning is paramount, as it significantly influences the efficacy of the MEWL framework. The query options and ground truth results demonstrate the framework's capability to correctly identify materials based on word inputs, showcasing its potential in enhancing word learning models. By refining the understanding of word meanings through their material properties, the MEWL framework aims to improve the efficiency and accuracy of machine learning algorithms in natural language processing. The MEWL framework is a novel approach to understanding object representations and motions. A crucial aspect of this framework is the introduction of several key concepts, including Uptalters, motionsrec, ArXiv, Aning aus, and Manafad. These concepts are mapped to specific word concept pairs, enabling a more nuanced comprehension of object representations and motions. Additionally, the framework incorporates URSA-STU and OUTSAPAC, each with its respective word concept mapping. These concepts play a vital role in elucidating the complexities of object representations and motions within the MEWL framework. The Uptalters concept, for instance, is essential in capturing the dynamic relationships between objects, while motionsrec facilitates the analysis of motion patterns. ArXiv, on the other hand, is critical in understanding the spatial relationships between objects, whereas Aning aus and Manafad provide insights into the temporal and causal aspects of object interactions. The incorporation of these concepts into the MEWL framework enables a more comprehensive understanding of object representations and motions. By mapping these concepts to specific word concept pairs, the framework provides a robust foundation for analyzing and interpreting complex object interactions. This, in turn, has significant implications for various applications, including computer vision, robotics, and artificial intelligence. Overall, the MEWL framework offers a novel and powerful approach to understanding object representations and motions, with its unique set of concepts and word concept mappings providing a rich framework for analysis and interpretation. In the realm of machine word learning, the concept of MEWL is explored. This page presents a series of queries and their corresponding options, along with ground truths and word concept mappings. The queries are designed to test the machine's ability to understand and differentiate between various words and concepts. The first query involves the options: Wise Vikit Missenings, Wise Vikit Renalsit, Nesselkro Renalsit, Men Parning Sorpar, and Men Parning Missenings. The ground truth for this query is Men Parning Missenings. The word concept mapping indicates that Men Parning corresponds to the color gray, Wise Vikit to brown, Nesselkro to blue, Sorpar to a cube, Missenings to a cylinder, and Renalsit to a sphere. The second query includes the options tonalol priorlik, tonalol set listen, tonalol retalness, berdako priorlik, and berdako set listen. The correct answer is berdako set listen. The word concept mapping for this query shows that berdako represents a cube, parshaisic represents a cylinder, tonalol represents a sphere, set listen corresponds to the color purple, retalness corresponds to cyan, and priorlik corresponds to blue. This page demonstrates the complexity and nuances of machine word learning, highlighting the challenges in creating a system that can accurately differentiate between words and concepts. The use of queries, options, and word concept mappings provides a structured approach to evaluating the performance of such a system. The machine word learning (MEWL) framework is designed to learn word meanings from visual and linguistic contexts. In this section, the authors evaluate the MEWL framework on a series of relational reasoning tasks. These tasks require the model to identify the correct word concept mapping from a set of options. One example illustrates the MEWL framework's ability to learn spatial relationships. The query, blue cube menuum gray sphere, is evaluated against 5 options, with the correct answer being blue cube menuum gray sphere, which corresponds to the word concept mapping, menuum, behind. This demonstrates the model's ability to understand spatial relationships and map words to their corresponding concepts. Another example showcases the MEWL framework's capabilities in learning word concept mappings. The query, yellow cylinder denkarens purple cube, is evaluated against 5 options, with the correct answer being yellow cylinder denkarens purple cube, which corresponds to the word concept mapping, denkarens, behind. This example highlights the model's ability to generalize to new words and concepts. The word concept mappings learned by the MEWL framework include menuum, behind, minvis, front, medlito, left, denkarens, behind, paisika, right, and denbepi, front. These mappings demonstrate the model's ability to learn nuanced and context-dependent word meanings. The relational reasoning tasks presented in this section demonstrate the MEWL framework's ability to learn and generalize word concept mappings from visual and linguistic contexts. The results suggest that the MEWL framework can effectively learn word meanings and apply them to novel contexts, highlighting its potential for natural language understanding and generation applications. In the context of machine word learning, this page presents a series of queries and their corresponding ground truths, along with word concept mappings for each term. These queries are designed to test the model's ability to understand spatial relationships between objects and their attributes. The first query involves the terms ensazonpen, pressmankan, ortiv for nestorma, citedso, and debeti. These terms represent different shapes, colors, materials, and sizes. The ground truth for this query is citedso behind ortiv for, indicating that the model should understand the spatial relationship between these two objects. The second query involves the terms onalde, warderenair, agetalvi, tedfakal, and difficalo. Again, these terms represent various shapes, colors, materials, and sizes. The ground truth for this query is tionciono right agetalvi, demonstrating the model's understanding of spatial relationships between these objects. The word concept mappings provided give insight into the attributes associated with each term, such as shape, color, material, and size. For instance, ensazonpen is mapped to a small, cyan, rubber sphere, while pressmankan is mapped to a large, green, rubber sphere. This page highlights the importance of understanding spatial relationships and object attributes in machine word learning models. By testing the model's ability to correctly identify these relationships, researchers can assess its performance in comprehending complex queries and generating accurate responses. The MEWL model, a machine word learning model, utilizes a word concept mapping technique to understand the relationship between words and concepts. It assigns unique identifiers to each word or concept in the text. The model has identified 6 concepts: ur, manth, ricide, mentmo, torden, and sakal. For instance, the word torden corresponds to concept identifier 5, and kovning corresponds to concept identifier 1. This technique allows MEWL to differentiate between words with similar meanings based on their context. The model's performance in accurately identifying word concept mappings demonstrates its potential in natural language processing tasks. This final segment of the research paper on machine word learning delves into the pragmatic and semantic aspects, aiming to establish a robust mapping between linguistic expressions and visual concepts in an artificial intelligence system. The novel concept, MEWL, machine word learning, is introduced as a means to enhance the understanding of word meanings within machines. This is achieved through the development of a pragmatic model that integrates both semantic and syntactic information into the learning process. The experimental setup employs a combination of linguistic and visual inputs to train the model, utilizing a dataset consisting of various objects with distinct shapes, colors, and sizes, accompanied by descriptive sentences that convey these attributes. The performance of the model is assessed using standard evaluation metrics such as precision, recall, and F1 score, which are commonly used in natural language processing and computer vision tasks. The results of the experiments are visually demonstrated in tables and figures, showcasing the effectiveness of the approach in learning word meanings from both linguistic and visual cues. Notably, the model exhibits significant improvements in understanding complex concepts such as spatial relationships and object properties. An analysis of the limitations of the current approach is provided, highlighting potential areas for future improvement. The need for more diverse and challenging datasets to further refine the model's capabilities is acknowledged. The paper concludes with a summary of the key findings and contributions made by the study, emphasizing the importance of integrating both linguistic and visual information in machine learning models to achieve a deeper understanding of word meanings. Potential applications of the work are suggested in various domains, including robotics, image captioning, and question-answering systems.